professor. I represent one of the members of our group, André Gil, and my paper is about cloud native applications and cloud migrations, the good, the bad, and the points between. So, cloud native features have come a long way, and normally cloud native features come with many advantages, but they also come with a cost. This cost will vary depending of our application and the data that it uses. Sometimes, and as we are going to see, sometimes maybe going cloud native is not the best an option that makes sense. So, the good, the bad, and the points between. The pros. As you can see from this third slide, the good parts of an application going to the cloud is that it can take full advantages of cloud native features. This will provide a boost in performance comparing with non-native features. As I said before, the boost in efficiency with cloud native features and APIs translates to a better performance and, as it logically it implies a lower cost. This cost topic we will talk about a bit later, since it's not as linear as the other advantages of going cloud native. For last, the scalability. While writing apps to the cloud, you have full access to the auto scaling and load balanced features of the cloud platform, one of the strongest points of the adoption of this technology. Having talked about a bit of the good parts of this technology, unfortunately, we have to address the downsides of it. There are trade-offs to the cloud-native applications development and designs. The biggest one is that you are giving a portability, since applications that are made native for specific clouds are not portable to others, locking you to the cloud provider, which allows an enormous leverage for these companies that provide the basis for our applications. Developers are getting good at placing the cloud native features into a specific domain, which allows to more easily change cloud providers if necessary. For last, we have to talk about standards. Since it's a new technology, standards are not generally implemented, which is aggravated by a lacking of guidelines about best approaches and cost effective. For our fourth slide, we have but talking about the good and the bad. So, what are our options if we choose the path of migration? And should we migrate? Well, as I represent in our presentation, we have 7 R's displayed in the slide for each application, and each represents a path that we can take to migrate our application to the cloud. Based upon its immediate as well as long-term, we can choose to migrate the cloud, but we have to think about long-term advantages, short and long-term advantages. In some cases, you need to break the application apart into reusable components, and in other cases, application can be replaced with software as a service or SaaS applications. Those applications are not compatible and will need a full rewrite to migrate to the cloud. This will be unfortunately, it will be the most cases. The toughest part of migrating a application to the cloud is figuring out one of these correct paths, the 7 correct paths. The retire part is usually one of the path is retire, which is all. It should be obvious, which is obvious from the start. If an applications are moved to the cloud, how should they be and how? If an application is moved to the cloud, how should it be configured, changed, or not? We have to keep in mind that when migrating to the cloud, we have to do this with the heart of a financial officer, chief financial officer, and not and not from a technology or a software engineer, because at the end of the day, the costs is what matters, and not what is technically superior or what we want. Thank you.
Okay, for this part of the presentation I will talk a little about microservices architectures enables DevOps. This paper describes how the team behind the mobile software named Vectory migrated the monolithic software into microservices. And why? Well, this brings many benefits, providing the adaptability to technological changes and, most important, to reduce time to market and better development team structuring around services. Microservices architecture is a cloud-native architecture where each service is independently deployable and it can run in its own process while communicating through lightweight mechanisms such as RESTful API. Vectory was originally a relational database management system functioning as a service. Developers that have no acknowledgement of server-side programming use this service that provide to them a development kit for their target platforms such as iOS or Android. Vectory was migrated to microservices for different reasons: the need of reusability, the need for decentralized data governance, need for automated deployment, and the need for built-in scalability. The new technology used for the new architecture of the system includes Spring Boot embedded application, OS environment variables for configuration, and Spring Cloud Context and Spring Cloud Config Server to separate the configurations from the source code as continuous delivery practices recommend. They also use Netflix open source software to provide microservices specific components, and also Spring Cloud Netflix integrated with the Spring Framework. For the service discovery, they used Eureka. For the load balancer, they choose Ribbon, and Istrix as the circuit breaker and Zool as the edge server. As you can see in this slide, we have the initial architecture of the Vectory before the migration at your left, and the architecture after the migration at your right. The migration was not one-step procedure. They performed it incrementally without affecting the end users. They start with continuous integration, letting developers integrate their work early and regularly. That helps preventing future conflicts. For this goal, they choose Jenkins as the continuous integration server and GitLab as code repository and Artifactory as the artifact repository. For the service deployed, they choose Docker registry, so each service could be deployed independently. All tests were replaced with independent tests for each service, decreasing inter-team coordination, and with these changes was possible to bring DevOps practice. Continuous deployment was introduced to separate environment specifications, source code, and configurations. That way they could evolve independently and making Docker image produce the same behavior in different systems. They also created a cluster of CoreOS instances containing Kubernetes. Then they deployed their services independently from each other. They also changed the team structures into functionally separated teams. They applied DevOps. Each team was responsible for a service containing people with different skills, development and operation. In this way, they could make more frequent releases of new features to production.
Now, I'm going to talk on a practical approach that I've found and that I've chosen for this presentation. So, we know that nowadays many financial exchange markets are based on a system known as high-frequency trading. This enables trades to be fulfilled electronically at superhuman speeds. One major challenge is how to test robot traders in a realistic setting, where not only its intelligence but also its ability to perform under non-zero latency environment is tested. Most stock market traders can be tested on a real-world financial exchange, where there's serious financial risk involved, A market simulator where the actions have an effect on a market, however, it's a synthetic market and as such not so realistic. Or a legacy real-world market data where actions won't affect the market. Another major difficulty is the fact that most market simulators are either designed to run on a single machine or on LAN, where there's effectively zero latency between traders and exchange. A good example of this is the Bristol Stock Exchange. My chosen paper presents a distributed market simulator called Distributed Bristol Stock Exchange, or BDSE, that is based on the Jane Street Exchange Market, publicly available in 2nd of February of 2019, whose scheme is displayed here in the slides. The most important part is the matching engine, or ME, which is a single monolithic machine that holds the exchange orders and identifies the buy and sell orders. Also, it sits on a strictly managed private network. Next comes the cancel ferry and the auction ferry. The first is solely responsible for managing the cancel orders, which are orders to cancel all the client's live requests, and the latter aggregates any orders and runs an optimization to find the price that maximizes the shares traded. When completed, these shares are returned to ME. Retransmitters, or RTs, account for the losses due to the use of UDP multicast by resending lost messages. The client porter is responsible for accepting connections to individual clients and provide mechanisms for them to perform transactions with the ME, such as placing orders, requesting quotes, and receiving execution reports. The drop port is similar to the client port. However, it accepts connections from institutions known as clearing firms, which are third-party transmission managers. The trade reporter listens to all trades that occur on the ME, anonymizes the data, and publishes it on an external trade reporting firm. At last, the market data publisher listens and anonymizes all market data on the ME. It then uses UDP multicast to transmit the data to a network of clients. During the development of the BDSE, two commitments were done. The decision of using the FIX protocol, which is used as a de facto standard by thousands of financial institutions and exchanges. FIX is a large and complex language with many different types of messages, and while it will provide BDSE with a realistic protocol, it will increase the complexity. Basically, FIX is a bit of an overkill. The second commitment, which is more of a compromise, it's the fact that UDP unicast protocol had to replace multicast, since AWS doesn't support the multicast method at the time of writing the paper. The only downside is that the exchange publisher must iterate through each client in turn, sending them market data. So, after the development of the project, it's time for the results. So, the tests were divided in two parts, one called latency tests and another called race to market experiment. Latency tests involved testing varying latencies for clients positioned around the globe. All clients were timed from how long it takes for them to receive market data. Also, trading clients from around the world were used for this experiment, since it wouldn't be possible to test if a trading agent's profitability was dependent on its ability to race to market. The graphics seem to confirm that latency indeed increases with geographical distance, which was to be expected. Both the server and clients 1 and 2 are located in London, whilst client 3 is in the USA, more specifically Ohio, and client 4 is in Australia. All values were to be expected, except for client 3, which had an inconsistent variance and standard deviation. These latencies suggest that Amazon handles more spikes in traffic between London and Ohio. These results really show that UDP unicast is definitely a perfectly viable option for transmitting market data within Amazon's network to clients spread across the globe. Finally, in race to market experiment, a trader can steal the deal if they learn how to respond to a market change before a competitor. Therefore, the further you are, the longer for that client to receive market data, and as such, the less profitable a client is. As you can see, both figures indicate that indeed the furthest you are, the less profitable you are. Results also show that there is much to explore about algorithmic trading.